Hello everyone. Today I would like to present supervised pun detection and location with feature engineering and logistic regression. So what is a pun? Let's look at the example. I used to be a banker, but I lost interest. Puns are a type of wordplay that deliberately exploits two or more different meanings of the same or similar words in a sentence, and often explores humor. In this example, the word interest is the pun word. The first meaning is related with bank, and the second meaning is about curiosity feeling. Second example, an evil wild beast bad news. The news here could literally mean news or bad news. Different to the first example, this type of puns use different words with similar soundings are called heterographic puns, whereas the first type is called homographic puns. Puns are widely used in literature since a long time ago. They could be very helpful, especially to non-native speakers. If such systems could detect puns are embedded into machine translation someday. What we want to achieve in this project is not just to build a system and see how good it is. Instead, we also built a dataset for pun detection regarding the fact of limited training data, as well as tried to unveil how puns may work according to their types. To solve this problem, we explore different feature sets as input for logistic regression, and measure their influence in terms of assigned weights. The feature sets could be grouped into four categories. First is part of speech tag. By analyzing the dataset, we found that if a sentence is known to be a pun, there are 98% chance that the pun word is a noun, a verb, an adjective, or pronoun. Besides, a verb-type pun word is almost certain to appear at the end. Second is to represent the entire sentence. To do this, we used Dr. Weg and BERT models as the contextual background for disambiguation. The third one is also at the sentence level, but we treated the sentence into two parts. Some researchers believe, and this is also our hypothesis, that the pun word often locates in the later half of the sentence. Here is how we did it. Dependency parsing. For example, the heat from the gunman in the sauna where they could sweat it out. In this example, after applying dependency parsing, we can see this subtree here, where they could sweat it out, and we extract this as a later and important part that may contain the pun words, and then take the rest of it, the heat from the gunman in a sauna, as the first part. The fourth one is word embedding, or its meaning. In this case, we used GloVec and other approaches like path distances of word stances in WordNet for pairs of words. Here is the feature set for pun detection part. We did experiments for both types of puns on two different settings, one with 5-fold cross-validation and the other one only with the collected training data. For the 5-fold cross-validation, we randomly split the dataset provided by SemEval, then tested each fold independently, and calculated the macro score in the end. Thus, the final results cover all benchmark data with 5 sub-experiments. For the second setting, we generated a corpus from the website Pun of the Day with mixed type of puns. After removing duplicates and fit the dataset by limiting the range of word counts, we ended up about 700 pounds and a variety of negative samples made of non-punning jokes, famous sayings, and other short collections. From the features listed here, feature 4, 5, 6, 8, 9, 10, and 12 give positive influences on the final results. In the ablation test, we found that the major factors are sentence representation, feature 4 and 12, the relation between both parts, feature 5, 6, and 10, and word meaning, feature 8 and 9. While the sentence representation offers the basis, the relation between both parts also helps in general or individual word pairs. We further inspected the weights of all feature vectors. Since all features have different dimensions, feature 12, sentence representation using birds, occupies more than 2/3 of the feature space, and most of the top 15% important components are from this feature. Feature 8 is about the similarity to idiomatic representation. The third parameter in it is to calculate the maximum ratio of overlapping words to the word length of the found idiomatic representation. And this parameter always has the largest influence. Then comes feature 4, direct sentence representation, and sometimes feature 6, direct for both parts of the sentence. Similarly, we tested some features for location of puns. In this task, we only experimented 5-fold cross-validation with the same setting from pun detection. Here are the features we used. All the features are word-based and each assigns a vector or value to words. In this task, we added homonymic information. That's feature 2, same pronunciation, and feature 4, comparison of the similarity of a word and its homonyms to the content words for heterographic puns. From the ablation test, we found that both feature 6, position of the word, and feature 7, part of speech tag, lead to a significant increment in the result. They gave words, especially content words, which locate at the second half of the sentence more weight. Feature 10 concatenates the global vector to represent the word itself. It results in a 7% boost. Feature 3 uses doc2vec to extract relation between separated parts, while feature 9 is to use mask LM and find out the surprise if a word is unmasked. Together, they contribute to around 2% improvement. These two features answer to our hypothesis that the pun word often locates in the later half of the sentence. They also tend to focus on the differences between double meaning of the trigger words and the two parts. As you can see, we try to add homonymic information for heterographic puns, such as F2. It helps, however, it still left much to explore for several reasons. First, the data is heterographic instead of homophonic. For example, orifice and office. Second, variances of the word are not considered. For example, knowingly and know. Third, puns may expose name or compounds. For example, clearance and clearance. Such words are rare and sometimes even made up. But in our model, this problem is remedied by adding word frequency feature, feature 5, instead of giving special attention to particular names or structure patterns. Although this feature works significantly in heterographic, It barely influences the homographic ones. Unlike heterographic puns, one needs a word with two senses that are widely known to people in homographic cases. So a rare word can hardly be used in that situation. Here are the results of our system compared to other published systems till the date of our submission. The two tables on the top is for detection task. The first setting is five-fold cross-validation and tests all data provided in the original task. The second setting is the one using our own training data and does not use any data from the task for training. From the results, our first setting leads to the best scores. Our second setting also outperforms all the teams which does not use official data for training. That's the teams masked with color blocks by about 4%. Besides, we can see a 5% performance drop from training in the five-fold cross-validation to the self-collected corpus. This may result from multiple reasons. For example, the collected corpus does not categorize the pawning types. The non-pawning samples may consist of some hidden pawns. The two corpora vary in terms of their properties, etc. The two tables at the bottom is for location task. For location on homographic pawns, our model's performance is lower than the systems which use long short-term memory. Added pronunciation features, it exceeds the best results by around 5% for heterographic pawns. While preparing the final version of this paper, we found out two more papers that are published concurrently. One reaches similar results as ours, and the other one surpasses our system. This, on the bright side, proves the popularity of this topic. To wrap things up, we provide a dataset from pawns detection and built models that achieve the state-of-the-art on three subtasks for different types of pawns. More importantly, we found that three things affect a pawn: general interpretation of the content, relation for both parts, and word meaning. In case we know it is pawning as a priori, we can utilize, for example, word position or surprise according to their type to locate the pawning word. And also, for heterographic pawns, people sometimes use rare words to achieve similar pronunciations, but homographic pawns usually use very common words, so that both meanings of the words are known to people. So this is my presentation. Thank you very much for listening.